The objective of this lecture is to provide the first part of the description of an orbit as a function of time. Now, as I said, this is the first part. So this is actually going to be the first part of a two-part sequence. So this is going to be part 1 of 2. And in this first part, the goal will be to introduce a key quantity, which is called the eccentric anomaly. And the key part of this lecture, the goal of this lecture, will be to relate the eccentric anomaly to the true anomaly. Now, if you recall, for an orbit, we're dealing with an elliptic orbit here. So on an elliptic orbit, the angle of reference, which is used to describe the position of the spacecraft, is the true anomaly. So if I have the focus of the orbit at point O, and I have the position of the spacecraft labeled as point S, the position of S relative to O, that distance, is actually R, and the angle between the eccentricity vector and the position of the spacecraft relative to the focus is the true anomaly, which is nu. So, which is nu. Now, in order to introduce the eccentric anomaly, I have to draw two circles. The first of these two circles is a circle that is tangent to the ellipse at both periapsis and apoapsis and circumscribes the ellipse. So that circle looks as follows. Now, on that circle, I'm going to label a couple of points. The first of these points is going to be A. A is directly above S, and it lies on this outer circle. Now, A is a point such that if I take the center of the circle, which also happens to be the center of the ellipse, so if I move these labels just a little bit so that we have them nice and clearly defined relative to where those points are, there's a chord from C to A. So from C to A, this chord is drawn as so. Now, if you take the angle between the x-axis, and remember that the eccentricity vector lies along the direction px, where px is the first direction in the perifocal basis. The angle between the direction px and the line connecting C to A, or the vector from C to A, that angle is defined as the eccentric anomaly. So E is the eccentric anomaly. And again, recall that nu is equal to the true anomaly. Now, using this information, we can actually start describing E in terms of nu. We need one other thing in order to be able to do that. And that is, as I said, there's that first circle circumscribes the ellipse. Now I'm going to have a second circle. What the second circle is going to do is it's going to be tangent to the ellipse at the top and bottom of the ellipse. And so it actually looks, and it's inside. So the ellipse circumscribes, if you want to think of it that way, the inner circle, or the inner circle is inside the ellipse. So the way that the inner circle looks is as follows, is that if you draw a circle that is such that it is tangent to the ellipse at the top and bottom of the ellipse. That's what that circle looks like. Now there's a point on this ellipse, which actually, on this inner circle that lies along the chord connecting C and A, and that point is actually going to be labeled B. Now, the interesting thing about point B is not just sort of randomly on this inner circle anywhere, but it's actually at the same height or same level away from the x-axis as is S. So as a result, we can actually describe this in a nice compact way using distances now. We're going to actually put a bunch of distances together on this diagram using what's here. We need one other value in order to be able to do this analysis, which is that directly below A and S is a point which I'm going to label D. So D actually, A, S, and D all lie along the same line. A, B, and C all lie along the same line. And B and S both lie along a horizontal line that's parallel to PX. So in other words, if you draw the vector from B to S, that actually is in the same direction as PX, which is also in the same direction as E. So we're going to put down a bunch of distances now to make all this work. Starting with the center of the ellipse, we have the distance from C to A is actually equal to A, which is the semi-major axis. The distance from C to B is equal to B, which is the semi-minor axis. Now we're going to go from C along the x-axis or along PX to get the distances from C to O and C to D. So C to O, that distance is actually equal to A times E, where E is the eccentricity of the elliptic orbit. Now, the distance from O to D, this is where things start becoming in terms of the true anomaly, which is that if you note that the distance from O to S is R and the angle between PX and OS is nu, then that means the distance from O to D has to equal R times the cosine of nu. All right? Now, that gives us everything horizontally. Now we're going to go vertically, which is that you note that the distance from D to S is equal to R times the sine of nu. It's kind of the same analogy as what we had with the horizontal distance. But because the distance from D to S, because B and S are along the same horizontal line, which means they lie along the direction PX, that's also equal to B times the cosine of, B times the sine of E. So if you look at this right here, you see that R times the sine of nu has to equal B times the sine of E. Now, the last part of this is that you'll see that the distance from A to D, so I'm going to do AD, that's equal to A times the sine of E. Now from here we can actually start relating R to nu. That's the first part of this. So now relate R to E using the distances shown previously. So how are we going to do that? So now let's look back over here for just a minute. So we can see that the distance from C to O is AE, and the distance from O to D is R cosine nu. So that means that the distance from C to D is equal to the distance from C to O plus the distance from O to D, which is equal to AE plus R times the cosine of nu. But we already knew that the distance from C to the distance from C to D, we can also get that. Let's put that down here. The distance from C to D is equal to A times the cosine of E. So as a result, this is equal to A times the cosine of E. Now, the next part's actually a little bit easier because we know that the distance from D to S is r sine of nu, which is equal to b times the sine of E. So we also have r times the sine of nu is equal to b times the sine of E. So let's put these two equations next to each other. So we have AE plus r cosine of nu is equal to a times the cosine of E. We have r times the sine of nu equals b times the sine of E. So that's fairly helpful, because now what we can do is, if we can somehow get this all in terms of a, we can eliminate b. But we have a way of being able to do that, because we know that the semi-major axis is related to the semi-minor axis through the relationship that b squared equals a squared times 1 minus e squared. So now what we can do is, let's take these two equations and let's solve for r cosine nu and r times the sine of nu. So if I take these two equations and I solve them for r cosine of nu and r times the sine of nu, I get the following results. I get a times the cosine of E minus ae, which is equal to a times the cosine of E minus E. And the other equation just stays exactly the same. I get b times the sine of E, but that now is equal to a times 1 minus e squared to the 1/2 times the sine of E. So now you can actually see that I can take the sum of the squares of both sides, and I'm going to eliminate nu from the equation completely. Because if I take the sum of the squares on this side, I've got r squared cosine squared nu plus r squared sine squared nu has to equal a squared times cosine E minus little e squared plus a squared times 1 minus e squared times sine squared E. So now the left-hand side just becomes r squared. So we wind up with r squared is equal to. So now let's look over here. We've got a squared that comes out of the whole thing. So we wind up with a squared times cosine of E minus little e squared. That's the first part. And then we've got plus 1 minus e squared sine squared E. So now let's expand out the entire right-hand side of this. This gives a squared times, we've got cosine squared E minus 2e cosine of E plus e squared. And then we've got plus sine squared E minus e squared sine squared E, which is equal to, well, if you look at the picture here, the equation here, you've got cosine squared E plus sine squared E. So that gives you 1 minus 2e cosine of E plus e squared minus e squared sine squared E. But this can be written as follows, which is that you see that there's an e squared in the equation over here. So we wind up with an a squared times, now what we wind up with is 1 minus 2e times cosine of E, and then we get plus e squared times 1 minus sine squared E. But 1 minus sine squared E is equal to cosine squared E, so we get 1 minus 2e cosine of E plus e squared times cosine squared E, which is equal to a squared times 1 minus e cosine of E squared. Which, now, there are a couple of things that have to be noted here because we're dealing with an ellipse, right? So we know that 0 is less than or equal to e is less than 1. So that implies that 1 minus e cosine of e has to be greater than 0 because we know that the cosine function goes between negative 1 and 1, and there's no way that this can ever be less than 0. Furthermore, we know that the radius has to be positive. So as a result of all that, we wind up with the fact that this thing will always be positive. This quantity will be positive when I take its square root if I just retain the positive square root. So as a result, we wind up with r is equal to a times 1 minus e cosine of e. So that's the first result. We now have the radius in terms of the eccentric anomaly. So notice that we've eliminated the true anomaly from this expression, and we just have it in terms of the eccentric anomaly. So the next thing to do is we're going to use this result together with the previous equations that we developed. Notice that the two previous equations were the ones that were outlined here. So if you recall, we had two equations. Perhaps it would be better to put this in red. Two equations here, right? So what we can do is we manipulate those two equations, which gets us to these two equations right here, and we can get a relationship for the cosine of nu and the sine of nu. So the first of these is going to use the cosine of nu. So recall that r times the cosine of nu is equal to, well, what do we get? We got a times cosine of e minus e. But we have an expression for r now, right? We know that a times 1 minus e cosine of e times the cosine of nu equals a times the cosine of e minus e, which implies that the cosine of nu is equal to cosine of e minus e all divided by 1 minus e times the cosine of e. But we notice in the earlier expression, again going back to what I marked here in red, that we also have an expression here that involves the sine of nu. So it's also useful and important to be able to get an expression for the sine of nu. But we know that the sine squared of nu is equal to 1 minus the cosine squared of nu. So let's use the fact that we have an expression for the cosine of nu to now get us an expression for the sine of nu. So therefore, we have the following. Sine squared nu is equal to, well, it's 1 minus cosine of e minus e all divided by 1 minus e cosine of e, the whole thing squared. So now let's manipulate this equation into a different form. So therefore, sine squared nu is equal to, well, we know the denominator is going to be 1 minus e cosine of e squared, so I'm just going to put the whole thing over that. 1 minus e cosine of e squared. And in the numerator, well, since the first term is 1, it's going to be 1 minus e cosine of e squared. And then we've got minus cosine e minus little e squared. So now let's expand out the numerator. So because the denominator is whatever we still have, it doesn't change. So if I expand out the numerator, which may require me lengthening this fraction line a little bit, I get 1 minus 2e cosine of e plus e squared cosine squared e. And then I've got minus. Now I've got cosine squared e minus 2e cosine of e plus e squared. So that can now be rewritten as 1 minus e cosine of e squared. And now let's expand this out. So we've got 1 minus 2e cosine of e plus e squared cosine squared e minus cosine squared e plus 2e cosine of e minus e squared, which is equal to, we've got 1 minus e cosine of e, the whole thing squared. And now you'll notice that the 2e cosine e and the minus 2e cosine e cancel out. So we wind up with 1 minus cosine squared e, and we've got plus e squared cosine squared e minus e squared. So let's manipulate that a little bit more. So therefore, sine squared nu is equal to, well, again, the denominator doesn't change. It's 1 minus e cosine of e, the whole thing squared. And the numerator, we've got 1 minus cosine squared e. And then, now what we can do is we can factor out the e squared out of the second term with a negative sign. So we've got minus e squared times, and if you look, what's left over is 1 minus cosine squared e. So that just becomes 1 minus cosine squared e. Well, let's do it the other way around, which is that you wind up, well, that's okay. 1 minus cosine squared e, this is fine, times 1 minus e squared, all divided by 1 minus e cosine of e, the whole thing squared. Now, 1 minus cosine squared e is just sine squared e. So this equals sine squared e times 1 minus e squared, all divided by 1 minus e cosine of e squared. Which implies that the sine of nu is equal to 1 minus e squared times, the square root of 1 minus e squared times the sine of e, all divided by 1 minus e cosine of e. So now we have two expressions. Let's get both of them together so that we can use them in conjunction with one another. The first one is the cosine of nu. So the cosine of nu is equal to, let's go back and get it from earlier, cosine e minus e over 1 minus e cosine e. And then we have the sine of nu is the last expression that we just got, which is the square root of 1 minus e squared times the sine of e, all divided by 1 minus e cosine of e. Now together, we can actually use these expressions to get a relationship between the true anomaly nu and the eccentric anomaly e as follows. But we need a trigonometric identity in order to make this happen. So the trigonometric identity that I'm going to use is as follows, is that we note the following, that the tangent of theta over 2 is equal to 1 minus the cosine theta, all divided by the sine of theta. If I substitute that identity using the angle nu, that implies that the tangent of nu over 2 is equal to 1 minus the cosine of nu, all divided by the sine of nu. Well, let's start making the substitution now. If we make that substitution, we get the tangent of nu over 2 is equal to we've got 1 minus, well, the cosine of nu. That's the cosine of e minus little e, all divided by 1 minus e cosine of e, all divided by the sine of nu, which is the square root of 1 minus e squared times the sine of e, all divided by 1 minus e cosine of e. Now, perhaps it's a little better to write this again a little bit bigger on the next page. So we're going to get the tangent of nu over 2 is equal to, let's just write it bigger so we can see it a little more clearly, 1 minus cosine e minus e, all divided by 1 minus e cosine e, and the whole thing is divided by the square root of 1 minus e squared times the sine of e, all divided by 1 minus e cosine of e. Now, again, let's put everything over a common denominator. So the denominator stays the same. It's 1 minus e squared sine of e, all divided by 1 minus e cosine of e. But the numerator is now put over 1 minus e cosine of e. And that numerator then becomes 1 minus e cosine of e minus cosine of e minus e, from which we can actually cancel the 1 minus e cosine of e in both the numerator and the denominator to just get the following fraction, which, if you notice, you've got 1 minus cosine e, and then you've got minus e cosine e, and then plus e, all divided by the square root of 1 minus e squared times the sine of e. So now, this tangent of tangent of nu over 2 then becomes, well, if you look here, you've got 1 minus cosine e, and then the second term, you can factor out an e, and you've got plus e, again, times 1 minus the cosine of e, all divided by the square root of 1 minus e squared times the sine of e, which simplifies to the following result. You've got the tangent of nu over 2 equals, well, the 1 minus cosine e factors out, so you wind up with 1 plus e times 1 minus the cosine of e, all divided by the square root of 1 minus e squared times the sine of e. But the denominator, because it's 1 minus e, there's a square root of 1 minus e squared, can be rewritten like this. You get 1 plus e, all divided by the square root of 1 plus e times 1 minus e, and then you've got 1 minus the cosine of e, all divided by the sine of e, which can be rewritten as follows. Well, because you've got a 1 plus e over the square root of 1 plus e, the whole thing becomes the square root of 1 plus e, all divided by 1 minus e, times 1 minus the cosine of e, all divided by the sine of e. So this is the tangent of nu over 2. But we had an identity that we used previously, so recall that the tangent of theta over 2 is equal to 1 minus the cosine of theta, all divided by the sine of theta. So that implies that 1 minus the cosine of e, all divided by the sine of e, is equal to the tangent of e over 2. Now, that gives us an expression, interestingly enough, in terms of the half angle of the true anomaly, the tangent of the half angle of the true anomaly, in terms of the half angle of the eccentric anomaly. And that's the expression that we get. Now here is a place where we have to be a little bit careful when we actually figure out the angles themselves. This is a relationship between the tangent of nu over 2 and the tangent of e over 2. But what we're really interested in is we're interested in nu, the relationship between nu and e directly, not just the tangents, right? So in trigonometry, there's a way to be able to take inverse tangents in such a way that we actually get all 4 of the quadrants taken into account in the process of doing this. And that construct is what's called a 4-quadrant inverse tangent. Now the 4-quadrant inverse tangent differs from the standard inverse tangent in that it takes into account the signs of both the numerator and denominator. So in a standard inverse tangent, if we have, say, if we say that tangent of theta equals y over x, I'm just using y and x generically, then this would give us theta is equal to the inverse tangent of y over x. But note that because the tangent function itself is only defined on negative pi over 2 to pi over 2, this would result in theta only being on negative pi over 2 to pi over 2. But the trouble with that is that the true anomaly, you recall, the true anomaly, nu, is on 0 to 2 pi. It has all 4 quadrants, right? So you can't just deal with the third and fourth quadrant. You have to have all of the quadrants, right? So this is on the interval 0 to 2 pi. And since we need to deal with all 4 quadrants, we cannot use a standard inverse tangent to be able to relate nu to e. So a standard, that's what's called a standard inverse tangent, is insufficient So we need what's called the 4-quadrant inverse tangent. Now the 4-quadrant inverse tangent works as follows. If tangent of theta is equal to y over x, we individually take into account the signs of both y and x, and we get theta is what's called a tan 2 of y comma x. And it turns out that if we do that, we wind up with the following result, which is that we wind up with theta being on the interval negative pi to plus pi. So that actually helps quite a bit because now we have swept out all 4 quadrants. Of course, the problem with this is still that we're not on the interval 0 to 2 pi, but that can be fixed afterwards. So the way we do that in this particular case is let's go back to this expression that we have for tangent of nu over 2 and its relationship to the tangent of e over 2. We've got the square root of 1 plus e all divided by 1 minus e times the tangent of e over 2. So the way we can do that is we can actually write, because remember I have a y and an x, a numerator and a denominator, so I can write the numerator part as the square root of 1 plus e times the sine of e over 2, and the denominator part is the square root of 1 minus e times the cosine of e over 2. Now, if I sort of generically term the numerator, I'm just going to call the numerator here, this part I'm going to call it y, because that's what I called it before, and I call the denominator part, I call it x. Then what we can do is we can take the 4-quadrant inverse tangent, and we get nu over 2 is equal to a tan 2 of the square root of 1 plus e times the sine of e over 2, and the square root of 1 minus e times the cosine of e over 2. And this right here now gives us a way to be able to compute the four-quadrant, the true anomaly. So therefore, the true anomaly is equal to 2 times the four-quadrant inverse tangent of, I've got the square root of 1 plus e times the sine of e over 2 and the square root of 1 minus e times the cosine of e over 2. Now let's observe a couple of things, which is that the eccentric anomaly is on the interval 0 to 2 pi. So if it's on the interval 0 to 2 pi, that implies that e over 2 is on the interval from 0 to pi. Well, if e over 2 is on the interval from 0 to pi, we know that sine of e over 2 is greater than or equal to 0 when e over 2 is on the interval from 0 to pi, because we're in the first and second quadrants. So as a result, this calculation is always going to wind up giving us the right result. What it's going to give us is, because the cosine switches sign when you go from the first quadrant to the second quadrant, but what we're going to wind up with is, we're going to wind up with this a tan 2 part. It's going to be on a tan 2 of the square root of 1 plus e times the sine of e over 2, and then the square root of 1 minus e times the cosine of e over 2, before I multiply by 2, will be on 0 to pi. But then we're multiplying by 2. So that implies that nu, which is equal to 2 times the four-quadrant inverse tangent of the square root of 1 plus e times the sine of e over 2, and the square root of 1 minus e times the cosine of e over 2, that will actually be on the interval from 0 to 2 pi. So we wind up with the correct quadrant. Now we have one more thing that we need to do, which is we need to do the inverse calculation. So the inverse calculation is the one where we get the relationship between get the eccentric anomaly in terms of the true anomaly. We need to go both ways. So let's go back to this last expression that we've got here. We have tangent of nu over 2 equals the square root of 1 plus e over 1 minus e times the tangent of e over 2. Now, if you just flip the calculations, this is actually not very difficult to do, but it's important to do it, which is that tells us that the tangent of e over 2 is equal to the square root of 1 minus e over 1 plus e times the tangent of nu over 2. Now, we can do the same thing we did before, which is that we can do the four-quadrant inverse tangent, which is that we get the tangent of e over 2 is equal to the square root of 1 minus e all divided by times the sine of nu over 2, and then the square root of 1 plus e times the cosine of nu over 2, which then gives us that e over 2 is equal to the four-quadrant inverse tangent of the square root of 1 minus e times the sine of nu over 2, and then the square root of 1 plus e times the cosine of nu over 2. Now, again, we multiply by 2, and we wind up with e is equal to 2 times the four-quadrant inverse tangent of the square root of 1 minus e times the sine of nu over 2, and the square root of 1 plus e times the cosine of nu over 2. Now, if we go through the same argument that we went through before, we know that nu is on the interval from 0 to 2 pi. So that implies that nu over 2 is on the interval from 0 to pi. But the sine is always greater than or equal to 0 on that interval. So sine of nu over 2 is greater than or equal to 0 for nu over 2 on the interval from 0 to pi, which means that this is going to wind up giving us the right result. Immediately we're going to wind up with a tan 2 of the square root of 1 minus e times the sine of nu over 2 and the square root of 1 plus e cosine of nu over 2. That will be on the interval from 0 to pi, which implies that nu, which is equal to 2 times a tan 2 of the square root of 1 minus e times the sine of nu over 2, and then the square root of 1 plus e cosine of nu over 2. That will be such that e is on the interval from 0 to 2 pi. So we now have a relationship. So we now have relationships between the eccentric anomaly and the true anomaly. These relationships, just to summarize the whole thing, I want to make sure that we summarize what we've got, is that nu is equal to, well, let's go back and get the last thing. Well, yeah, we can do it in either order. Nu is equal to 2 times the inverse tangent of the square root of 1 plus e times the sine of e over 2, and then the square root of 1 minus e times the cosine and e is equal to 2 times the 4-quadrant inverse tangent of the square root of 1 minus e times the cosine sine of nu over 2, and then the square root of 1 plus e times the cosine of nu over 2. These two relationships are essential in being able to compute the orbit as a function of time, because we need to go back and forth between the eccentric anomaly and the true anomaly. So this is the last point before this lecture ends, and then we move on to the next set of the material, is that it is essential to be able to go back and forth between nu and e. So sometimes we're going to actually need to be able to compute nu given e. Sometimes we're going to need to be able to compute e given nu. And in fact, when we actually compute the orbit as a function of time, we're going to figure out everything in terms of e, and we're going to go back to nu. But initially, we're going to be given everything in terms of nu because we're given position and velocity, which means we're going to convert to orbital elements. So we're going to always start with nu, convert to e, do all our calculations in e, and then convert back to nu. Of course, that process may not make any sense at this point because we haven't done the second part of this, which is when we're actually going to introduce Kepler's equation, and that's going to use the eccentric anomaly. But at this point, we have these two relationships that we can use to establish the next step, which is how we actually work with both the eccentric anomaly and the true anomaly when we're actually solving for the position as a function of time. So for right now, we're gonna end this lecture, but keep in mind these two relationships are of utmost importance when we actually work with the next steps in the calculations. So keep these ready and handy when we need them in the latter part of the analysis. So for now, we're going to actually stop this lecture, and that's where it ends, and we'll move on to the next part of the material in the next lecture.